The next talk is given by Johannes, and it also will be some part of tutorial. So it will be, Johannes will explain you what consensus testing mean, how it's related to this post-Chen theory. And yes, Johannes is from the Technical University of Munich. He was my PhD student until I left Munich to Braunschweig. So we still work together. Now he is as Holger Boch's chair. And he's also working on quantum information theory, on post-Chen theory. And yes, today he will talk about consensus testing. And I think we should do it like in Paul's case. If you have a question, please interrupt him. So I think it's really, yeah, it's really good to interrupt him in the beginning, not then ask at the end. I didn't understand your slide 3, and because then you won't understand the rest. So it's really, we are not so many people. You just can interrupt and ask if there is some misunderstanding to avoid that. Okay, then Johannes, the stage is yours.
First thing I do is I correct myself. So the first mistake is on the first slide. That's you have to add Christian there because that's the title slide from the Globecom talk, and he joined for the second part, basically. Like part 1 is correct, but for part 2, Christian is in there. So consensus testing is basically a sort of identification, and you will soon see why. I just give my introduction. Beating Shannon. So, of course, we talked a lot about beating Shannon in the molecular communication part. And so what do you have to do if you want to beat Shannon? That's a fundamental limit, what he proved. So how can we get better? We have to make the problem easier. So otherwise, fundamentally, it's not possible. And Yaya showed that identification is easier than decoding. That was the title of his paper. So you've already seen that identification is somewhat easier than decoding in the sense that it's more efficient. You need to know less. And on the other hand, identification is super specific. So you only find out, is this or not? You can't do a lot with it. With transmission, when you know the message exactly, you can do anything with it. So I think it's interesting and important to look at variations of identification, and this is one. So consensus testing via a relay. We have a relay network, so we have 2 nodes, Alice and Bob, and they can communicate over a relay Rudy in memory of Rudy Alswede. And so we set up this communication in 2 rounds. So first round, they send to the relay. Second round, they send back. And they want to test consensus via this relay. So each knows a message. And in the end, they want to know, do we have the same message or not? So this is like identification, but in a slightly more complicated network. So here on the right side, you can see the network unfolded in time. So it's basically the protocol. First, they both encode, send it over the uplink channel, which may be 2 independent channels or not. Then there's a recoder. So what Rudy does is recoding. There is a downlink channel, and we have 2 decoders. You see a line from each message to the respective decoder. That's because, of course, Alice doesn't forget her message after encoding it. So Alice can also use it in the decoder again, her message. And the same for Bob. In the end, they each do the test. Are the messages equal? And so such a code consists of 2 encoders, a recoder, 2 decoders, where the probability that the test has the same output as the true comparison of the messages has high probability. So if we hide somewhat, for example, the encoder of Bob, then we see it's, in this case, it's basically just an identification. In the other case, it's also basically just an identification, where in between we send via the relay. But we do both at the same time. So this really is the error probability for identification, what you see there, if it's only for one test. Now, a naive approach to coding for such a network could be we just do a linear network coding and we send our stuff over that. So actually, this project was inspired by a talk from last year, or it was kind of started as a fusion of my talk from last year and of Pitt's talk from last year about physical layer network coding in molecular communication, where it was linear network coding. So what one might want to do is there, if you have an additive channel, the output in the end is the addition of the two inputs with each uplink noise, this ZU, and a downlink noise in the end. The receivers can just subtract their message, in this case, if it's additive. And then, basically, the channel becomes a single user channel. So then you're at identification. Easy. So that's our baseline to compare the performance with. So here you can see somehow in these pictures the time that you need for running the protocol. So you have Alice who transmits T to the relay and Bob as well. And in the second round, they both transmit the sum of what was transmitted downwards. This needs the same time to transmit the point-wise sum, so the letter-wise sum. And in the consensus testing, so you can just use a transmission code to transmit the messages and transmit them down, and then you can compute it. So that's one version. You can use a consensus testing code, or in this case, basically an identification code, on top of this linear network coding over this single user channel then, and you get, in principle, the same picture, but with reduced times that you need. On the other hand, we propose a better protocol, and you'll see that it's better. So decode and forward 1 bit. So why shouldn't the relay already do the test if they're equal or not? And then the relay just has to send down the result. It's 1 bit, so you can encode it in basically no time. You don't need relevant block length, so negligible block length to just send 1 bit reliably. So then the rate is completely determined by the uplink rate, because the other part is negligible asymptotically. And this looks, if you do it with transmission like that, so you can transmit to the relay can decode, the relay can do the test. Now, can the relay also do it more smartly? This would look like that. And yes, it can. So later I will explain you how you do it exactly. It's basically almost like a normal deterministic identification code. Here we have the results, including the scaling. So I won't talk about rates here, but this is just how the code scales. So the rate is, for example, in the central column, okay? In the central column, the rate is just the log Q, for example, like this R in this general formula. So in the left two columns, it's 2 to the MR. So we have exponential scaling in the third column for the Gaussian channels. As for deterministic identification, we have this M to the MR or 2 to the M log MR scaling, when M is the total block length. And with total block length, I mean the sum of the block lengths of the uplink and the downlink, because this is the time that you need in total for the protocol. And in our case, the uplink time is always basically the same, or is the same for the same type of code. So whether you use a transmission code, linear or nonlinear, it's basically the same. And for a consensus testing code, linear or nonlinear, it's the same. But depending on linear or nonlinear, the downlink time varies. Because if you do linear network coding, you will have the same downlink block length as you have in the uplink. Like after the linear combination, you have the same length of your vector as before. And the nonlinear, so therefore our protocol is nonlinear, where you only send down 1 bit. You can see here that therefore the linear and the nonlinear have a factor of 2 difference in the usage of the block length n. So if you need no time basically for the downlink in the nonlinear protocol, but the same time for the downlink in the linear protocol, then you need double the time at least for the linear protocol. And then we have the respective rates with that scaling. So we have here SAR and so on. These are Shannon capacities, so the transmission capacities. So for the linear network coding, it's just determined by the rate from A to B and from B to A. So because you get these single user channels from Alice to Bob and from Bob to Alice. So and since your code book is determined by the worst performance, the size of your code book, because both have to be possible, then the minimal rate determines your performance. And for the nonlinear protocol, it's determined by the rates from Alice or Bob to the relay, basically. For consensus testing, you can see that the rate is constant for the discrete channels. So here we have a QSC, query-symmetric channel. So for certain types of channels, we know the exact capacity there, and for others, we have bounds. And for the Gaussian channels, also we have the classical deterministic identification scaling, which doesn't depend on Shannon capacities or so. Here is an example where we just calculated curves for a BSC with error probability 1/50, so binary symmetric channel. Each bit is flipped with a probability 1/50. So this is the GlobeCom slide, kind of, because you need such a plot for GlobeCom. And you can see, basically, transmission is worse than consensus testing, and linear is worse than nonlinear. So that's basically what you can see in this plot. And our proposed code is in both cases better. Here, these are the block lengths that you need to achieve a certain code size in comparison with the different protocols again. So basically, I just plugged in numbers in the formulas from the table before. And there you can see also that for relatively short block lengths, you get like a factor of 4 to 5 or so, or like, let's say 3 to 5 in difference between the different protocols. So ours are clearly the most efficient. On the other hand, when you have short blocks, so you don't need so long blocks, you may not have a good error. And here in this plot, you see that maybe when you want to have an error probability of 1%, you have to go above 2 to the 10 or so block length, so above 1024 or something. On the, I'm sorry, I don't have the curve for transmission now for the optimal error exponent, because only I just shortly before thought it might be interesting to look at the error for the talk. But let's say to have a good error performance, you have to go somewhere above like 2 to the 10 or so. We saw that it's better what we did than our naive approaches, but that doesn't tell there is not a better approach. So we want to know, of course, it's optimal, and it is. And the proof is actually quite nice and easy, because you can just trace it back to an identification problem, so deterministic identification. So if we just, in the picture before, cut off the second decoder, so it's irrelevant now, we only look at the performance for the first one, and we move out these encoders and the uplink here. The uplink is optional, it may also still be in there. Then the new second box, the dashed box, this is basically just a decoder for a deterministic identification code. So here we have an encoder, a channel, and the other message is known by the decoder. So that's exactly the deterministic identification setting. Problem, the decoder is stochastic. Intuitively, this shouldn't help, like noise in the decoder shouldn't help. And we also have a proof for this, general one. So in general, for every function that you want to compute, stochastic decoding doesn't help, except if you have constraints that you have to have distributed decoding or something. So that's in the reference to in this paper. So therefore, we can just use the identification upper bounds as upper bounds for this consensus testing. So in the Gaussian case, we will get this 1/2 as upper bound for our rate in the right scaling. For discrete channels, we just get this cardinality of Q, so of the alphabet, as in the deterministic identification setting. Now to the code. We can build it. And we can build it with real codes, not only with random coding. So we just take a code with a linear Hamming distance. I mean, you've heard a lot from Pau, for example, about how to construct deterministic identification codes. And I'm now so I'm looking at simple channels now, so discrete channels or Gaussian channels. And there, basically, what you do is you just need a linear code or you just need a code with a small distance, but a linear distance. And you can, for example, just take a Reed-Solomon code, or Ilya Vorobyev made a construction where you don't need so large fields by using concatenated codes. And then you just do a distance test at the receiver. So classically, for deterministic identification codes, you test the distance between your code word and the received sequence, and you test if it is close to the expected distance that you have for this channel. In our case, we just test the distance between the two channel outputs and test if it's close to the expected distance. So for two parallel channels, this works. And so this delta here is just the expected relative Hamming distance. This T is kind of a distance typical set. That's why I use this letter T. So it's quite like typicality, and Hamming distance and typicality is also very much related. So for binary, it's basically the same. And the decoder is just typicality, like distance typicality decoder. And this applies to more general than binary or Curie symmetric channels or so. So we have this reliability criterion 3. So if basically it's always more likely that it's further, like it's more likely to be, the channel output is more likely to be closer to the original code word than further, or if it's the other way around, that it's always more likely to be further than closer. At least in these cases, one can show that one can choose the epsilon suitably such that this decoder will be reliable. So we have this probability that it's typical. So the probability that it's typical is high. And then you can also choose your decoding radii basically such that you will get non-intersecting or almost non-intersecting typical sets there. So this can be both built for real, like the Reed-Solomon codes, for example, you can build them, but also the decoder. Usually one says a typicality decoder, you can't build it because for transmission, you need exponentially many typicality tests, but here you don't. So for symmetric channels or for constant composition codes or so, basically you only need one typicality test done, or one distance test. Now, to summarize this part for deterministic identification or deterministic consensus testing, we have an optimal scheme that is decode and forward 1 bit, basically. The codes are implementable. You can just implement them and use them. Just as an outlook, this works also for more edge nodes. So we can just do pairwise tests, basically. So we can just take multiple nodes as well in a star network. We are much better, so we have much larger codes or shorter block lengths than naive approaches. And so here you see the slightly more general version of what I showed you in concrete numbers. So the capacity of the network, basically, for this consensus test is lower bounded by the capacity of only the uplink. That's what we used in the achievability. And it's upper bounded by the deterministic identification capacity of each uplink. And in many cases, they coincide. So for example, for Curie symmetric erasure channels, Gaussian channels, for binary adder channels, so where the channel adds the things in the end, because this addition is basically already a part of the distance test. So it preserves this distance test, Gaussian adder channel as well. So these are the examples that we explicitly derive the bounds for in the paper. And what we would like to have is matching bounds for more channels. Maybe we can generalize it completely to all the channels from your paper, basically. and have a very general condition or when the bounds coincide. And stochastic encoding will be part 2. So that's because we know, of course, that we can achieve probably a lot more with stochastic encoding. But the question is, are the protocols as simple? Now, if we go to stochastic coding, things get a bit more complicated because we have additionally in our picture the randomization. So this is the same slide as before, only with randomization. So you see this L and S. L stands for local randomness, and L1 is only connected to encoder 1 and to decoder 1, of course, because Alice doesn't forget her local randomness. The same for S, for shared randomness. Alice doesn't forget her shared randomness, so it's connected to decoder 1 and also to decoder 2. So we assume that the randomness is shared between one encoder and the other decoder. And the shared randomness S2 is shared between the other encoder and the first decoder. And they could be correlated. So there can be a common part, which is then also shared between both encoders. So I just try to have a relatively general form of connections between for the shared randomness. And it could also be connected to the recoder, but it doesn't help. So the error probabilities and code definitions except that are basically as before. So only the encoding is now stochastic, but our encoder in the picture here is still a deterministic function because we just moved the randomness out into this additional random source. So you can still imagine the network to be quite the same. Now, this time we talk about rates. So we don't have so many different scalings or different types of rates. Therefore, I'll just define what a rate is. Rate here is now doubly logarithmic because the codes with stochastic encoding for identification scale doubly exponentially. Now, we have two different types of rates because we might count different resources. So a rate is normalized, for example, over the block length. But in general, you can say it's just normalized over something, some resource that you have to pay for. So you want to know how much do I get for what I pay. And here we pay in block length for the first rate, in block length for the uplink and the downlink, n and k. But in the second rate, we also pay for the randomness. So we say we have a random generator and we can pull samples from it. And this is maybe also some resource that we want to count. So, and we weigh them equally, so we normalize over the sum of them. So this first thing we will just call the rate or the capacity, the respective optimum, and the second will be the common randomness assisted, or like with finite no, both can be common randomness assisted, but like I think we called it the common randomness consensus testing capacity. So it's kind of like a rate reliability or reliability rate function. We have an additional thing that that the rate depends on. And below this sigma is then the rate of our randomness, sigma u for sender u. So the shared randomness that sender or that Alice has is sigma 1 and sigma 2 is for Bob. We simplify again. So we consider separately the cases where we have only common randomness and only local randomness. We didn't consider the combination yet because before we can solve the local randomness case completely, it doesn't really give us insight, I think. As you've seen before, a randomized identification code or stochastic identification code usually is constructed by a hash function or so. So you hash a seed and the message, and you transmit the seed and the hash. Now, when you have common randomness, you can use that as the seed. So you don't have to transmit the seed anymore. You only transmit the hash. So can you guess how a protocol would look like, a sensible, with pure common randomness for consensus testing? We have the seed already distributed as common randomness, and we want to compare the hashes. If the hashes are the same, we say yes. If the hashes are different, we say no. What do? We just use our previous consensus testing code. So solved, basically. But we want to know the rates and the influence of the randomness. So in identification in general, we know that this scaling is not only doubly exponential, but the scaling is approximately exponential in the number of different random seeds if you have a uniform distribution of the seeds. So we assume that uniform distribution. So it's doubly exponential in the rate of the randomness, actually. And when we compute the different rates, we have this normalization. So to assess how this normalization converges and so on, we need to know the relation with the hashing rate. And so Christian, I think yesterday, for example, showed this, that you can use a hash that is like scales only with 2 to the square root n, and when the seed scales with 2 to the n. Therefore, we can say that that n is approximately of the order of square root s, and k is approximately the same order if we use a decode and forward construction. So basically, so if we use the construction from before, then k would be 1 approximately, or like negligible because we didn't need it. If we just use a transmission code underlying, even then k would be approximately n, and it would still be like asymptotically irrelevant compared to s. So therefore, so since s is approximately n squared, so n grows much larger than s, then s grows much larger than n and k. So therefore, the first capacity would be infinity. So you can say, if I can always pull more samples from my random source, I have an arbitrary amount of randomness available, so I can achieve arbitrarily much. I can be have arbitrarily large codes. But if randomness has a cost, then not. Kaspar. Yes, the lower one is with both are with common randomness, but the lower one, in the lower one we count the common randomness, and in the upper one we don't count it. So in the upper one, basically randomness is for free, and in the lower one, randomness has a cost. So
yes, okay. So we always assume that we have created common randomness either for free or by paying for it before the actual consensus testing begins.
yes, it's pre-shared, so it's non-causal common randomness.
Okay, because otherwise I was wondering how Rudy can determine anything, because if the code words are not based on the same randomness, it would need to recover more like the respective code word, right?
Yes. If Rudy wants to recover, no, let's say if Rudy wants to recover, we need common randomness shared in the beginning.
Exactly.
Only we don't need it to be shared with Rudy, but we need it to be shared between Alice and Bob.
Yes,
So,
yes, Rudy doesn't need it, but
yeah.
if Alice and Bob have not agreed on a random position, then Rudy cannot decide anything, because they're not necessarily the same hash value, right? Because okay.
Yeah. So
now I'm back on board. Okay.
Yeah. For this, so for Rudy to be able to decode, we need common randomness shared between Alice and Bob, what I told you before, when S1 and S2 agree or have a part where they agree. Because then both can compute the hash with the same seed. And on the other hand, if they don't, you can also do the completely dumb solution, basically just take any transmission code with a bad rate, because your n is small compared to the randomness size. So your hash is small. You can still be arbitrarily good with the help of the randomness, basically, by just transmitting everything. And then we use this connection from S1 to D2, for example. So we just do an identification in the end. We just compare the hash at decoder 2, for example. So decoder 2 has the same seed as encoder 1. So decoder 2 can also check the hash. In the case where randomness is for free, as we see, we get infinite capacity then. And when randomness costs something, so we also count it in the rate, we normalize also over S. This S divided by N plus K plus S converges towards 1 because N and K are negligible. And so the rate, the identification or the consensus testing rate that we achieve will be the minimum of the randomness rates. The minimum because, again, the worst performance determines the size of our, or the number of messages that we can work with. The other case is we have only uniform local randomness. So in this case, we don't share anything before, but the randomness also has to be transmitted. Now in this case, can the recoder, can Rudy do the test? Question. Who believes it? Let's make a poll. Who believes that that we can just run the same protocol basically as before, as deterministically, so that we test at the relay and we send down 1 bit. Compression impossible, I say. Yeah. So this picture on the right is general. This is just, we have a channel from M to X. We have some other channel from X and Y to the N to something. If this channel together, if this picture is able to compute any function, basically reliably, any function of M and another argument, then this inequality below holds. This is also from this paper that that showed that the decoder can be de-randomized. So this relation tells us that the output of E, so this set of the axis, must be at least as large as the input, like the messages, plus something that vanishes asymptotically, or that is quite small. If the y to the n is exponential, so the y to the n is here much smaller than the m. So if I'm a bit more precise, we don't know that this m cannot be compressed for any function, but if it can be compressed, then this is already a deterministic compression. So basically there are 2 different messages m, which are always mapped to the same, so we can just reduce our message set. So this is like a trivial reduction. So apart from a trivial reduction, you can't compress the message by any doubly logarithmic rate if the other argument is already compressed to be exponential, or to be asymptotically much smaller than doubly exponential. So compression is impossible in quite general. So also for consensus testing, and therefore the recoder can't test. Therefore, we need a different protocol, and the protocol we thought of is just basically transmitting and doing a usual identification on top of this. So the bounds that we get are basically decode and forward bound for multiple access channels and or for relay channels like multiple access and the broadcast channel in the end, with the difference that we force both rates to be the same of the multiple access channel, for example. So there you usually have 2 rates. This third constraint would be times 2 a constraint on the sum rate. So if the rates are equal, then we get the constraint just halved. And since in the uplink and in the downlink, if we transmit our pair of seed and hash, we need the same cardinality. Therefore, the block length times rate of both has to be the same, like of the uplink and the downlink. And if we just do some manipulation, like just solve the first equation for k, insert it into the second, like for the rate, then we get the right-hand side. So that's just a manipulation to get rid of the block lengths in the rate expression. And then, so this R up is the uplink rate, like the rate that you get for a multiple access channel. And the downlink is the rate that you get for the broadcast channel. So these are really the capacities when you have to have the rates to be the same of the two inputs to the MAC or of the two outputs of the broadcast channel. For the upper bound, we do the same thing again. We trace it back to identification. We can do this if the uplink channels are, if we have two parallel independent uplink channels, then we can just upper bound it by the performance for one channel, because we just pull it out as in the picture, and then we just get the mutual information as an upper bound, because this is the capacity for single user channel identification, and we get the minimum again, because we always take the worst performance. So this gives us an upper bound, which coincides with this MAC capacity here in the case where the channels are independent. So in the case where the channels are independent, this expression for the MAC reduces to that. So in that case, basically when we have a perfect downlink channel, this would be optimal, and for two parallel uplink channels. But in the more general case, it's not. And we haven't been able to show it. Basically, what's missing is, if you look at the picture, we don't know for encoder 2 how much the other input to the channel, to the uplink of encoder 1 helps, how much this already computes, basically. I have a conjecture, basically, that it doesn't, so that you basically get a compound channel identification rate or something there, but this is just a conjecture for now. If that were true, we would have a matching converse. So to summarize everything, we have an optimal scheme for deterministic identification. It's decode and forward 1 bit, so quite trivial. We have matching capacities for lots of channels, and for more edge nodes, as long as they don't grow in the block length, it's all reliable. When they grow in the block length, then we have to look at things like k-identification. For the stochastic case, we can use deterministic consensus testing for the hashes if we have common randomness, because the seed is already distributed. For local randomness, the relay cannot test consensus at all, because you can't compress the other message, basically. You can only compress one from the doubly exponential into an exponential set. And therefore, our strategy is identification over a transmission code with a decode and forward transmission strategy. And this may be optimal. We haven't proved it. So the upper bound is open. In general, all those codes you can really build. So the deterministic codes, you just take a code with a linear distance, and you just do one or a few typicality tests in the end, or distance tests. For the stochastic codes, you learned in the last talk, for example, that they can now be realized really efficiently. And here, the encoders, they are just encoders for identification code. So this doesn't change because you're in this consensus testing network setting. Only the decoder changes a bit for the transmission part in the randomized setting, or to this other distance test in the deterministic setting. What's open is, of course, we would like to have matching bounds for more channels, and the converse would be nice. Of course, you can find other interesting directions from here. One might want to build it, really. Or like there can be other interesting network topologies. Like, for example, one could think of links between the edges, direct links, whether they help or not, or something, or some possibilities to make the relay adversarial or something. But so I think this is the first time, or the first example of identification in a more networked setting than just a one-directional one. So thanks for your attention, and I hope you enjoyed the movie and you have many questions.
Thank you. Okay, thank you for your nice talk and this results. Are there questions or comments? Yes.
I was wondering, so these are both extreme cases both, right? So either you just send the 1-bit result, which is in point-to-point identification, we always say this would be stupid, so we don't consider it, right? But here because we have the relay, we say, okay, now we do the identification at the relay and we send the results. So it's like super efficient basically. And if we can't do that, then we just have to transmit it anyway because we can't do anything about it. Do you think there are any situations where there's something in between? Like I'm not even sure what it would look like, or do you think it's like close to this scenario? It should always be either very simple or very transmission-y.
So you said that in identification, usually one says sending just the 1-bit is stupid. It's not stupid. If you can compute it, you should send it.
Yeah, I just meant it's not a hard problem,
But
so we
you
don't
usually
consider.
assume that the sender doesn't know the other message. And here we also assume this. The senders don't know each other's messages. So let's take the most general network here. I mean, encoder 2 doesn't know M1. So the encoders can't compute the message. But if the relay can already infer the message without paying any extra cost, it should do it. Rudy should do it. If he can't, he shouldn't, of course. And then let's say the results suggest, together with the conjecture, that it may be optimal to just put a stochastic identification code on top of a decode and forward transmission code. Decode and forward is here optimal because we don't have like direct channels. If we would have that, it would be different setting. If we would have direct channels between Alice and Bob as well. You could also, of course, consider like linear network coding here, but it would be worse because basically you have to correct the addition of the noise of the first and the second channel. And if you do decode and forward, you only have to correct the noise of one channel. But so it's not that transmission-y in the sense that you have to transmit the full messages, but it's transmission-y in the sense that you transmit the seed and the hash. So, which is much better. So you still get doubly logarithmic rates or doubly exponential codes.
Okay, thank you.
I don't know. I would answer a little bit different. So because I think you explain him what he asked. I think a little bit. I think the main thing you want to know is if there's something in between, then we can say theoretically no, because we have this theorem where you have that compression is not possible. So that means you have to send this because you cannot compression anyway. I think that was more or less his question, if there is something in between, but our theorem says no, there's nothing in between.
So the relay can't compute.
Okay.
The relay can't compute
Yeah.
anything to
Yes.
reduce the data, or to reduce the input it needs from the other channel. Yes. The only thing that we don't know is no, the encoder can't compress more. The relay might be able to compress something, so it might be that you can be more efficient on the downlink. That's what I said about this conjecture for the upper bound. So it might be that the relay, or already by coincidence, the uplink channel computes something, helps you solve the task. So it might be that you can compress after the uplink. Because the uplink computes already something. But without an additional input, so without an additional input, so this encoder E can't compress anything. If the recoder should in the end be able to compute the function, so to completely compress to the 1 bit. Yeah. So if R should be able to do it, or the recoder Rudy should be able to do it, then the encoder can't compress. So that means that Rudy would have to know exactly the message. So you would have to transmit the message to the relay so that the relay can compute it if you don't have common randomness or so.
Yeah, so I think, like, to frame it differently, I think I understand it exactly the same way as you. You want to compress as much as possible already at the senders, of course. And so either the recoder can compute the result for all of them or it can't. But it's, in general, it doesn't really make sense that there's more compression at the recoder, because you want to squeeze any compression that you can do already into the senders, because then you reduce the uplink, right?
Well, you would like to. On the other hand, the recoder has additional information because it has some information from both. So it might be that the recoder can compress something, and I don't have a proof yet that he can't, even if I believe that he can't. I believe I can prove it, but I can't do it yet.
Yes, I see. Okay.
That's
nice.
Just belief.
Thank you.
Actually, not a question. I just want to understand the model. So you are considering actually the identification problem over the relay network. So if you don't have, or there's no direct link from the sender 1 to from user 1 to user 2, no direct link, right? It has to be, everything has to go over.
Yes, they're forced to use the relay as if they were wired or something. Or if you're in a biological network, maybe you have 2 cells which communicate with each other, and you have some channel between them, which is the relay.
It's also in the communication network. You know, if we talk about the relay network, there is always a direct communication channel. Then you have also via the relay. So then the relay could help because the direct communication channel, you know, it's noisier or noisy. Then relay, maybe you get a better, you know, something, then you can forward or compute forward some information and to help the receiver to decode it. But here I see that the communication, everything has to go over the relay. There's no direct.
Yes, there is no direct path. And if you have a direct path, then I think in case the relay can compute the result, it would be more efficient as soon as the uplink channel to the relay is better than the direct channel. If the relay cannot compute the result, it might be different. Because then the relay, basically you have to pay for the downlink, which may change the picture.
Even this is without, but you are considering the channel actually to a relay, the uplink and downlink, they could be noisy, right?
Yeah, they could both be noisy.
Okay, good.
So in the case where, and the difficulty, so when you have parallel uplink channels, as we assumed for most examples in the deterministic case, then in the stochastic encoding case, with local randomness, the difficult part is bounding, having a bound in terms of the uplink channel. So like, and not in terms of the downlink channel, not the uplink, because it gets difficult as soon as you have any channel which has inputs from both sides. So as long as you can split your channel so that it can only has information from Alice or from Bob, so long the problem is easy to, or the converse is easy to get, but as soon as you have both, it gets difficult.
You introduce the correlation. So another one is it's just a comment. I think this model is like a mixture of this 2-party and the 3-party protocol. You know, I was presenting, because the relay could be like a linkage unit, really. And you get actually the challenge and your seed and hash from both. Then the relay actually could compute or could know it already okay. If I mean, especially
You
in noise.
mean the three-party protocol or what? Where you
Yes,
have an
yes.
additional
Yes,
unit?
yes.
Yeah.
But when you do nothing, you just forward, then it become a two-party protocol.
Yes.
That's where I see that this is like a mixture of, of these two-party and three-party protocol. Yeah. Okay. Thank you.
I was just thinking, like with these networked approaches, because it just moves away from this point-to-point aspect. I mean, K identification can be interesting, of course, but isn't there, I really haven't read about it any at all, but isn't there this concept of L source identification or something, where the sender has possibly multiple messages or something like this? Is this how it works? Or maybe I just say what I wanted to ask. So let's say Alice and Bob have two different messages, and they want to know if it's, or maybe you would need a third one. A third one would want to know if any, so if Charlie wants to know if Charlie's message is either Alice's or Bob's message.
So each of the three has a message, and Charlie wants to know if
either Alice or Bob has the same one.
And Alice and or Bob must have the same one, or what?
No, Charlie. So either Charlie equals Alice or Charlie equals Bob, but it's not exclusive.
Okay, and you can, and who can send to whom?
Yeah, they send via Rudy, I guess. I don't know. No, I'm just, maybe it's, yeah, maybe there's no answer there, but I'm just saying there are so many combinations there, like in terms of K identification, of course, but also in terms of exclusive or non-exclusive ORs, like when we talked about this fire sensor thing or something, it's really interesting in that dimension. If you want to know if any of them sees that there's fire or anything else.
In that case, Charlie is just Rudy. The fire sensor setting, yeah, I mean, of course, if you have a network setting where you send multiple messages over a channel, is more applicable to a setting where you have multiple sensors and you want to somehow fuse what they're producing. Yes. And on the other hand, if you want to, if you have many sensors and like if the number of messages is basically the number of sensors, then you and all sensors can be active at the same time, then you need a protocol with basically as many tests as you have sensors. And so you only get transmission performance basically then, because because basically you have to do as many tests as you have messages, and if you can do that reliably, it would enable you to decode. Yeah.
I'm aware that this addressing polling thing is like some people use it as a use case, but I know that it doesn't work. I was rather thinking about a sensor that has, I don't know, 1,000 or 1,000,000 states. So it has like a
Yeah.
grade for temperature, a grade for light, or even the color of the light and stuff like this, right? And it kind of concludes something that is not just its address, but some kind of observation of its environment or something like this. And then you want to find out, does someone think it's in this range or something? I just wanted to.
I think this could be close to K multiple object identification. So not K identification. So in K identification, you have the receiver selects K many messages and the sender selects one. In K multiple object identification, the sender selects K messages and the receiver can test if he's in the K set of the sender. But I'm not so familiar with the results of K multiple object identification.
One question. So when we started with this, right, it came by the inspiration of network coding, where you have this any network there you have any multicast network where you have multiple nodes transmitting and multiple nodes receiving, and then you want to understand what is the capacity of this network for that.
Yeah.
So do you see a way of extending this for this arbitrary network, for arbitrary multicast identification network where multiple nodes are
Multicast
sending?
too many end nodes also, or what?
Yes, where
Or
multiple
with,
nodes
like you have many nodes
sending
and you have
IDs.
some network in between.
Yeah, and then you have nodes receiving that each of them wants to identify things.
I think so. What you can't do is if A, B, and E, and if or if all these three, for example, should know what if they have the same. What you can't do is just compute equality here and just send forward the one bit here, because then D can't test if E is equal to any of the two. But also you don't have to forward both, because, for example, you can just forward one and if they're equal or something. No? Well, if they're not equal, you have to forward both, basically. No, if you're not equal, if they are not equal, it's sufficient to forward the 0. But if they're equal, you also have to forward the message so that D can test if it's equal to E, for example. So I think you can somehow benefit from it. What could also be something is that basically you get a tree structure where in the end this one computes one bit somehow, the one result bit, and here you need some intermediate results which are larger, and it could be that some linear network coding or some decode and forward, depending on the protocol, depending on if you have randomness or not, is optimal there. But I think somehow if in any protocol where you can compute it in the end somewhere in a node in the network, it would have a tree structure where you have a single node that can compute the result in the end. Otherwise, there is not really a way of reducing it to one bit in a lower layer of this, let's say. But so you can do something, and it's not completely trivial.
Okay, then thank you.